Hello, EE151. So for today, I'll be discussing fault analysis. Basically, I'll just introduce you to what is fault, then how do we analyze fault. On my previous video, natapos tayo on, actually it's a series of videos. Natapos tayo on doing load flow. So we performed Gauss-Seidel, we performed Newton-Raphson, and then we solved for the bus voltages using those two methods, and then using the bus voltages we determined the load flow. So that's basically what we did before. Now we'll be doing fault analysis. So I guess this is a series of videos ulit. I think I've done one before as an example lang kasi we're actually done discussing this, but I'm uploading some lectures para makapag-review kayo. Well, anyways, okay, so let's consider this system. I have here a generator and motor system. It's basically a generator source supplying a motor load 30 plus 40 MVA. Both of them are Y-grounded. Y-grounded muna tayo. I'll just introduce you sa fault analysis muna, and then later on we'll experiment on delta. Then these two are connected using a line between 1 and 2. So it can be a transformer, but for now we'll just use a line. So here, let's say that your motor is running at rated voltage. Therefore, the voltage at bus 2 is 1 angle 0. Okay, so it's running at rated voltage. So 1 angle 0 yung voltage sa bus 2. Now, for the single line diagram, take note that for fault analysis, at least for this series of lectures and on load flow then, we are dealing with the assumption here is that the system is balanced. Okay, so these methods are, well, the methods that I've discussed before are all applicable on transmission systems, but not yet on distribution systems, kasi distribution systems are highly unbalanced as compared to transmission systems. So this is for transmission systems. The system is balanced, therefore you can represent it as a single line diagram. Okay? So this is also the assumption for load flow, kasi dun sa load flow we also represent your network into a single line diagram na magagawa mo lang if your system is balanced. Okay, if your system is unbalanced, I think it would be best to represent it as in its 3-line diagram. But yeah, I think there are representations in IEEE connection diagram and then detailed in some other table yung connection the missing lines, like this, between these two buses you only have A and B, between these two buses you only have B and C, between these two buses you have ABC, neutral, etc. Okay, but for this example, at least for this discussion, we'll be dealing with balanced systems. So we may represent the network, this two-bus network, into a single line diagram. Okay, so I took the liberty of assigning values on the impedances. For the machines, generator and motor, I used J0.1 ohms per unit, J0.1 per unit for the impedance, and J0.2 per unit on the line. Okay, take note that I have here, this is the internal EMF of the generator. This is the internal back EMF of the motor. You have to include this. Of course, you don't have that when we're dealing with static loads, but since this is a motor, the internal back EMF would matter. I'll show that to you later on. Okay, so on the problem, it's stated that it is running at rated voltage. So the voltage at bus 2 is 1 angle 0. Okay, so we have the voltage at bus 2. This one. We have the voltage here. So the power here is given as 0.3 plus J.4 on 100 MVA base. Voltage power divided by voltage, then you conjugate that gives you the current at the motor. So now you have the current at the motor, and if you have the current at the motor, you can get the voltage drop here. If you get the current here, you can get the voltage drop here, and then the voltage here can be calculated as this voltage drop plus this voltage at bus 2. So that's basically this solution. Okay, so the current at the motor is 0.5 angle negative 53, and then by KVL I can get the voltage at 1 as 1.08 angle 3.18 degrees. So it's actually greater than the voltage at bus 1, and that makes sense. Okay, so this is basically simple circuit analysis kasi we have a very small network. It's just a 2-bus system, but well, if you really want, you can solve this using Gauss-Seidel or Newton-Raphson or any other load flow techniques. You can use that to get the voltages here. What I basically did was power flow. Okay, so it's basically power flow. I get the voltages, I get the current, and then we'll call this your pre-fault condition. The idea here is that this is the condition of the system before the fault happens. Okay, so I've been talking about fault a lot na, so I think it's time na introduce ko na sa inyo what is fault. The idea of a fault is that if you have you have three lines like this one. If you have 3 lines and this is your ground, it's like this one. Okay. Fault is when you have an unintended short circuit or open circuit between the lines and the neutral, or between any 2 lines or any 3 lines and the neutral. So it's basically that's basically fault when you have that short circuit for shunt faults and open circuit if it's a series fault. Okay, between your conductors and your neutral. So this is basically a fault. This one. This is a fault where all of my 3 lines are shorted and it is connected to the ground. That's basically called 3-phase fault. Okay. Well, it's very self-explanatory kung bakit siya 3-phase. Well, anyways, so for this series, I'll discuss shunt faults, and then later on we'll try incorporating series faults. Okay, but yeah. Well, for your examination naman, we'll stick with just shunt faults. Okay, so short circuits lang. Short circuits. Okay. So what will happen if you have the 3 lines ABC on bus 2 here simultaneously grounded? So all of them are shorted and then they are grounded. Okay, connected to the ground. Let's say maybe storm passed, then may natumbang puno. So natumba yung puno on those 3 lines. So all of the 3 lines are shorted, and then the tree, yung puno, is still planted sa ground. So you have the 3 lines connected to the ground. Of course, you have the impedance of the tree nung puno, but for now, let's just assume na wala muna siya. Wala muna tayong impedance ng puno. So let's just assume that it's an ideal conductor. Okay? So if all of these 3 lines are grounded, so the system is still balanced because all of the 3 lines are grounded. Basically, all of your phases are in the same condition. They are all grounded. Okay? Now, the single line diagram of the system will now look like this because all of them are grounded. Therefore, it can still be the system is still balanced. Therefore, you can still represent the system as a per phase in its per phase equivalent. So it's perfect per phase equivalent. Convert that to per unit, you have this single line diagram. So it's like this original system, but bus 2 is grounded here at this point. So that point is called your fault point. So this is called a symmetrical fault. Symmetrical siya because the system is still balanced, but it is faulted at the fault point P. Okay, so that's basically that's basically what is fault, excuse me, and that's basically your fault point. So we call this symmetrical fault because the system is still balanced. We have unsymmetrical faults, but we'll discuss that later. Unsymmetrical faults is when the fault causes the system to be unbalanced. So you have a balanced system, but when the fault happens, the system is now unbalanced. So yeah, we have that. So I guess yeah, that's it. That's for your introduction to fault analysis.